So how are we going to describe such a particle? Well, it's going to be moving along a line of constant theta and constant phi in the Schwarzschild metric. I'll remind you of the Schwarzschild metric. ds squared is equal to minus into 1 minus 2m over r dt squared, plus the same thing to the minus 1 dr squared, plus r squared into d theta squared plus sine squared theta d phi squared. If I want to find the geodesics, time-like geodesics, in this metric, moving along the lines of constant theta and phi, then it's just basically moving in the t and r plane, and I can find the geodesics by taking the action I is equal to minus 1 minus 2m over r t dot squared plus 1 minus 2m over r to the minus 1 r dot squared, and varying it to find the geodesic. If I do that, the first thing you'll notice is that because t is an ignorable variable, I should say dot here means d by d proper time. So the t equation of motion gives you a conserved quantity, usually called the energy, so that t dot is E over 1 minus 2m over r. Notice, of course, that this object, that E is conserved, really as a consequence of the fact that there is a killing symmetry of time translations. Otherwise, that would not happen. Now, what about the R equation? Well, that boils down to minus 1 is equal to r dot squared minus E squared over 1 minus 2m over r. But that's just basically the same thing as saying that UA is equal to minus 1, where UA is XA dot. So you need to integrate this up. R dot is equal to the square root of E squared minus 1 plus 2m over r. There's, of course, an ambiguity when you take the square root. This thing is supposed to be going inwards, so there is a minus sign here. Now what you have to do is to just integrate it. Integrating this equation is almost straightforward. The simplest thing to do is to do it by solving it parametrically. And if you integrate, let's suppose that this sphere starts off at r equals r0, so that's the initial radius of the thing, at rest. So now integrating this is straightforward, although not quick. R is equal to a half R0 into 1 plus cos of eta. Eta is a parametric variable, and it's related to the proper time S by R0 squared over 8m to the 1/2 into eta plus sine of eta. It's not a very nice eta. This should be cubed, not squared. Note that the total mass of this cloud of stuff is m is equal to 4/3 pi rho naught r naught cubed, this being the initial density. It is fairly easy to prove that the density remains constant as a function of time, or a function of s, or as a function of eta. And therefore, there is a chance that you will recognize this pair of equations. It's what you'd expect for the evolution of the radius of a Friedmann-Robertson-Walker universe populated by dust with closed spatial topology. So we can now fill in some gaps in the picture above. So what has happened here? Because of Birkhoff's theorem, you know that it's always going to be the case that outside this matter, the space-time will be Schwarzschild. But what's happening here is that there is gravitational collapse so that the ball of matter looks something like this. The metric inside the ball of matter is the same thing as a closed FLRW universe with k equals 1, filled with dust, but it stops at the surface of the body. So it's not the entirety of the S3, but just a part of the S3. What do you know about the FLRW models? You know that they create singularities when eta is equal to pi. So here is the analog of a Big Bang singularity. And because you know that outside the black hole, outside the collapsing body, the metric is exactly Schwarzschild, you know that this surface, where r is equal to 2m, where m is the m that we have up there, you'll form a horizon. So that's how you get gravitational collapse. Now, of course, you might be wondering, I've only told you what r is as a function of eta. perhaps it's important to understand what t is as a function of theta. And if you work it out, which requires a great deal of patience, t as a function of eta, so this is the Schwarzschild time coordinate of the surface. It's equal to 2m times the logarithm of the modulus of r0 minus 2m minus 1 to the 1/2 plus tan of a half eta divided by r0 over 2m minus 1 to the plus 1/2 minus tan of a half eta plus 2m times the logarithm of r0 minus 2m minus 1 to the 1/2 times eta plus r0 over 4m into eta plus sine eta. But to understand what happens in gravitational collapse, you don't really need to know this, just put it in for completeness. As an exercise, you should check that this really does solve the geodesic equations and reproduces the Friedmann-Robertson-Walker universe sitting inside the matter. So if you inspect this picture, there are various things that you might start to worry about. The first is a sort of historical fact. When this solution was first proposed, the obvious conclusion was, well, the singularities are all fake because you've assumed spherical symmetry forever, and therefore that's sort of an unphysical thing to do. So the question is this kind of picture where you have collapse forming a horizon in the middle of collapse and then having a singularity generic? Well, the answer to that comes in several pieces. This one. So, let's look at some of the consequences of this. The first is Penrose's singularity theorem. I'm not going to prove this. I'm merely going to tell you what it tells you. So it assumes that the energy density of matter is positive, it assumes causality, which I don't think that one really should be too worried about here. And it assumes that a horizon forms. Then Penrose proved that the resulting space-time is singular. Now there is a complication, and that is that for him, the word singular does not necessarily mean that the space-time has curvature that blows up. What he means by singular is that GD6 have future endpoints. But if you look at this picture up here, the GD6 that have gone inside the horizon will, if they're time-like or null, always reach the singularity and stop. So in that sense, Penrose's theorem clearly applies to this particular case. So for 2.5 pages in Physical Review Letters, you prove this and you win a Nobel Prize. The trouble is that the region where these endpoints happen might not be inside the horizon. So there's a second not result of Penrose. This is weak cosmic censorship. And again, I'll just state this in a it is the hope that the endpoints of these GD6 are inside the horizon. Another way of saying it is that an observer outside the black hole cannot see the endpoint. This is still a conjecture. There has been a fair amount of work recently on the topic due to Dafirmos and Rodniansky, Christodoulou and their collaborators, but it is still a conjecture and not a theorem. So the Hoope conjecture, Penrose's singularity theorems, and an assumption that weak cosmic censorship really works is what tells you that black holes really do form in gravitational collapse and do not produce naked singularities. But as you can see, two important pieces of that are still not proven, but are conjectures, although there's considerable evidence for them. So that's really all I want to say about gravitational collapse. I now want to move on to something a bit more general, namely what are usually called the laws of black hole mechanics. So let's start from some of the properties of the Kerr-Newman black holes. And we're going to assume that these are the only black holes that you can form, at least their equilibrium states. I don't think we have time to prove any of the more sophisticated or even the simplest no-hair theorem. So I'm going to assume the uniqueness theorems hold. They basically are consequences of Einstein's equations in the same way that Birkhoff's theorem is. So these represent stationary black holes. Formed after gravitational collapse. They are described, as we know, by three numbers: m, which we think of as the mass, q, which we think of as the charge, meaning electric charge, and a rotation parameter, a, which we can relate to the angular momentum, and this is equal to m times a. And being a black hole requires m squared to be greater than or equal to a squared plus q squared, so that you don't have a naked singularity space-time. Now there's some properties of black holes which are kind of useful. The first is the mass m. A conserved quantity is always associated with a killing vector, and there is a time translation killing vector d by dt. One way of describing the mass is to perform an integral of del A kb dsab over a sphere at infinity. And if I do that, I need a normalization constant, which is 1 over 4 pi. So that defines, in a rigorous way, what the mass of a black hole is. Although it's described at infinity, you could just as well do this on the horizon. So you can think of this, because we're in a stationary state, you can think of this as being rather like a Gaussian integral. So this definition of mass is due to Arthur Komar. So it's like a Gaussian integral. But I'm going to put it in inverted commas because this is not really a field strength tensor. Similarly, you can define the angular momentum. J, well, there is a rotational killing vector. D by d phi, ma d by dxa is equal to d by d phi. And there is a similar Komar integral for j. It's equal to 1 over 8 pi integral of del A mb ds ab. The factor of 2 here is just due to some strange definitions of how things actually get normalized. Another way of looking at this term is that it is effectively the same thing as G00. Sometimes called the time-like mass or the gravitational mass, as distinct from the ADM mass is what you get at space-like infinity. So those are two of the quantities. Then, of course, you can define the charge by an honest Gaussian integral. It's better. Q is going to be equal to the integral of FAB ds AB, this being the conventionally normalized flux tensor, and a factor of 1 over 8 pi. And again, that's over a sphere at infinity. Now, there are some things which you can derive from this. The very first is that linear combinations of k and m are also killing vectors. So I want to define LA to be Ka plus omega times Ma, where LA is going to be null on the horizon. Because in a black hole space-time, the horizon is stationary, you can, of course, say that there must be some killing vector associated with it, and this killing vector basically takes you up and down of the horizon. Depending on which sign you pick. But because it is null on the horizon, and neither k nor m are, except in the case of Schwarzschild, where k is, this thing, omega, defines an angular velocity of the black hole. You can evaluate it in the Kerr-Newman space-time, and it is equal to J over M times 1 over 2mr plus minus q squared. So that's one of the first things that you can define that has derived meaning. It's telling you something about the nature of the black hole space-time. Similarly, you can define an electrostatic potential for the black hole. If the black hole is sitting in space and you put the electrostatic potential to 0 at infinity, then you can define a potential phi and this is just the value of A and LA, this being the electromagnetic potential, but such that A at infinity goes to 0, so that this really measures the potential difference between infinity and the whole. Its explicit value in Kerr is equal to, in Kerr Newman I should say, QR plus divided by 2mr plus minus q squared. The next derived quantity I want to get to is the surface gravity Surface gravity is defined from the properties of L. Because the horizon is a null surface, if you sit on the horizon, you'll just stay on the horizon. So LA must obey the geodesic equation. On the horizon. Notice how we defined it. We defined it in terms of d by dt and d by d phi. So, if it obeys the geodesic equation, you'd be tempted to think that LA, del A, LB was going to be equal to 0. And it would be if it was affinely parameterized, but it isn't. It's proportional to LB, and the constant of proportionality is kappa, usually called the surface gravity of the black hole. It measures the amount by which the parameterization of L differs from being affine. There must be a word for this, I don't know what it is. Affineness. If this wasn't proportional to L, you'd have said, oh, that's some kind of force term. And that's where the word surface gravity comes from, because you think of surface gravity at least as being a force. But because it's proportional to L, it's not really a force at all. It's just measured by how much things are not affine. So, what is kappa? It is equal to square root of m squared minus a squared minus q squared divided by r plus squared plus a squared. The last thing I want to define is the area of an event horizon. The event horizon is a null surface, but if you fix some instant of time, then of course you can measure the cross-section. So this is the cross-section at fixed time on the horizon. If you're wondering which time coordinate, it would be the Eddington-Finkelstein type of time coordinate. And if you evaluate this for Kerr-Newman, you will get 4 pi, let's write it in a nice way, 16 pi into r plus squared plus a squared. But if you don't like it written like that, we can write it in a slightly different way. 4 pi into 2m squared minus q squared minus 2 times m to the fourth minus m squared j, is that really right? M squared q squared minus j squared. And again, you see that this thing doesn't make sense. This thing doesn't make sense unless m squared is greater than a squared minus q squared plus q squared. So those are some geometrically defined quantities. So let's use this to get to somewhere interesting. a different kind of chalk. So, we can now enunciate the laws of black hole mechanics. Zero, 1, and 3 are originally due to Bardeen, Carter, and Hawking. 0. Observe that kappa is constant on the horizon. Well, that was easy. 1. Suppose that I have a black hole in equilibrium with its surroundings with mass m, j, and q as its parameters. And I perform an infinitesimal transformation on the black hole so that m goes to m plus dm, j goes to j plus dj. Now, of course, j is a vector, so I'm going to assume that this is parallel to j. And q goes to q plus dq. Then you can derive what is usually called the first law of black hole mechanics. There are two ways that you can do this. Bardeen, Carter, and Hawking (1972) took the Komar integral m, which is 1 over 4 pi integral del A kb ds AB, and varied this expression. The result is incredibly complicated. We can do something easier. We can take A as a function of m and j and q, and just simply use the chain rule to work out a dA. So we would say dA is equal to dA dm dm plus dA dq dq plus dA dj dj. And if you do that and rearrange things slightly, you'll get the following expression. dm, the change in energy, is equal to kappa dA over 8 pi plus omega dj plus phi dq. This is usually known as the first law of black hole mechanics, by analogy with the 0th law of black hole mechanics. It looks awfully like the first law of thermodynamics. Here is an example of a missed opportunity. Almost everybody would say, oh, this represents the work done by speeding up the rotation of a black hole. This represents the work done by increasing the electric charge of a black hole. This represents a change in energy, and therefore a reasonable person would say, ah, that is TDS. But that's not what they did. It's even more puzzling because back in 1970, Bekenstein had realized that the entropy of a black hole should be proportional to the area, and therefore this thing should be proportional to the temperature, although he did not know the constants of proportionality. Hawking's attitude was, well, black holes are black, they have zero temperature, and therefore S is nonsense. There is no such thing as black hole entropy. To convince yourselves that there must be something like black hole entropy, you should consider the thought experiment of Wheeler and Bekenstein, fabricate a cup of tea, and throw it into a black hole. And if the black hole has zero entropy, you will have violated the second law of thermodynamics. So much for the first law. Let's see. The matter became even more puzzling because prior to this, Hawking had already found the Area Theorem. Let's call this 2. Crudely put, it says that if you throw something into a black hole, the area increases. The assumption is that the thing that you have thrown in has positive energy. Well, that looks awfully like the second law of thermodynamics. 3. The limit of kappa goes to 0 is pathological. Let me remind you that the third law of thermodynamics says that achieving temperature of absolute 0 in any finite number of processes is impossible. And that's rather like saying that the transition to extreme Kerr, where you have these degenerate horizons, is similarly impossible. So the laws of thermodynamics are staring you in the face, except that wasn't recognized at the time. And I must say I'm completely puzzled as to why it was not. So tomorrow we will see why they really are the laws of thermodynamics. We'll stop there. Thank you.
Yeah, thank you for the nice. Hello. Yeah, thank you for the nice talk. So, when you define the Komar mass, you defined it on two, surfaces. One was at spatial infinity, and the same was obtained also on the horizon, right?
Mm-hmm.
But I mean, the two surfaces at the spatial infinity and the horizon are quite different, and so are the nature of the vector fields.
Yes. So what happened is that Bardian and Carter and Hawking did it by looking at the Komar integral at infinity. But I think that is so complicated that I wouldn't want to present it. You can look in their work in communications in mathematical physics if you really want to see it. But given that we know the uniqueness theorems, why bother? Because it's simple. You just simply use the fact that you can write the area as a function of m and j and q.
No, I'm talking about the very definition of the Komar mass, where he said that the the area integral is the same.
Komar will give you the same answers whether you integrate at infinity or the horizon.
Okay.
That's true for M and for J. It's and the Gaussian integral that gives you the charge. Again, it doesn't matter whether you integrate that on the horizon or at infinity, you will always get the same answer.
Okay.
I would leave it to you to show that those integrals really do give you the M and the J and the Q. M and Q are easy, J is rather hard. You will find that an interesting challenge.
And for the weak censorship conjecture that you pointed out, I mean, is any energy conditions necessary for the space-time, or it's independent of any energy condition?
For the hoop conjecture.
No, not the hoop conjecture. The weak censorship.
Weak censorship. Certainly, the theorems of de Fermos assume particular forms of the energy momentum tensor. It would be nice to have something along the lines of saying that T00 is positive, but to the best of my knowledge, they haven't done that. Yeah, you can get rid of it.
Hello, here, sorry. I have a question on this Penrose singularity theorems. So, as you mentioned, these are really a statement about what happens to the curve. So, just like you said, for infalling or collapsing cloud of particles, it makes sense to say that it really, that singularity reaches, that singularity is what we expect. But say we have a Cauchy horizon or something like that. So then I guess we will only have curves of finite affine length. So then it means that for something like Kerr, it does not prove the singularity, or it says something else about the spacetime.
The Penrose singularity theorems tell you absolutely nothing about where the endpoints are. It just tells you that there are some.
Mm-hmm.
That's it. So, what your intuition is telling you well, perhaps singularities occur on the Cauchy horizon, and indeed, that's the kind of thing that de Fermos and his friends seem to find. But that doesn't mean that's a universal case, because they tend to be rather specific about the nature of the matter. So, I would regard that as an open question.
Uh-huh.
Of course, intuitively you say, well, they must end at places where there's essentially some kind of boundary. Mm-hmm. But that's a conjecture, not a theorem.
Yes, also I guess it does not help that this theorem is non-constructive. It's a proof by contradiction.
Yeah,
and maybe it would be worth looking for toy models where we can actually say which points are such that we cannot pass the curve.
Well, that's essentially what they do.
Okay.